I'll get started here. Let me start by making an attempt at a somewhat comprehensive list of derivatives.
We're not going to work on this one.
We're going to work on that. I just need to kind of make a point here about what we're doing. All right. So first of all, we learned that d dx of x to the n is n x to the n minus 1, right? The corresponding integration rule is that the integral of x to the n dx is x to the n plus 1 over n plus 1 plus a constant, right? And also the integral of dx over x, which is n equals minus 1, right, is the natural log of the absolute value of x plus a constant, right? So we have that. Let's see here. The derivative with respect to x of a to the power x, we learned natural log of a to the x, right? So the corresponding integration rule is that the integral of a to the x dx is 1 over the natural log of a times a to the x plus a constant, right? The reason for 1 over is if we differentiate a to the x, what happens? We pull down natural log of a, right? And so we need that 1 over log a to compensate for the log a that comes from differentiation, right? Of course, the most commonplace exponential function is what? Just d dx of e to the x, in which case we get e to the x and the same rule for integration, except, of course, we have to add a constant because it's indefinite integration. What else did we learn? Derivative of sine is cosine, right? Derivative of cosine is minus sine. Integral of sine x dx is minus the cosine of x plus a constant. The integral of cosine x dx is sine of x plus a constant, right? See, these are different, right? They're related, of course. Every one of these integration rules, if you differentiate the answer, you should get back to the integrand, right? Derivative of sine is cosine. Derivative of minus cosine is sine. Derivative of e to the x is e to the x, all right? What else did we learn about? How about cosh and sinh, right? d dx of cosh x was sinh x. d dx of sinh x was cosh x, right? So likewise, the integral of cosh is sinh, and the integral of sinh is cosh, right? But we also learned other things, right? Like so we learned the derivative with respect to theta of tangent theta was secant squared theta. We learned that the derivative of cotangent theta was minus cosecant squared theta. We learned that the derivative of secant theta was secant theta tangent theta. We learned that the derivative of cosecant theta is minus cosecant cotangent, right? Those are all basic rules of differentiation that we should know. you know? And each one of those pairs to a corresponding elementary integral, all right? Elementary integrals are ones that you should just know because they're basic to our knowledge of differential calculus. They're just educated guesses in reverse, right? So like when you see integral of secant squared, that is simply tangent of theta plus a constant, right? When you see the integral of cosecant squared, it's minus cotangent plus a constant. When you see the integral of secant theta tangent theta, d theta, you get secant theta plus a constant. When you see the integral of cosecant cotangent, you get minus cosecant theta plus a constant, right? Everything I'm writing on the board here thus far is what we would call, on the right-hand side, these are elementary integrals, all right? These are not things we're going to derive, they're things we're going to remember. You must remember at its base, the process of antidifferentiation is educated guessing. So we can't make educated guesses until we're educated, right? So I'm attempting to educate. We've seen all these derivatives before, right? But seeing them and remembering them are two different things, right? So, all right, so what else did we learn? We learned the derivative with respect to theta, well, let's say x. Derivative with respect to x of inverse tangent, 1 over 1 plus x squared. Derivative with respect to x of inverse hyperbolic tangent, I think that was, man, I can't remember if it's 1 over, anybody remember? I think it's 1 minus x squared. I say that because the range of the range of the hyperbolic tangent is between plus or minus 1, and it's an increasing function, so the derivative must be positive. That forces me to put 1 minus x squared. Anyway, d dx of inverse sine 1 over the square root of 1 minus x squared, all right? And there are more, right? But I think I'm going to stop here for our tables, all right? So what are these rules of differentiation? What do these inform us? These inform us about a few other elementary integrals. In particular, this one we read backwards, we see, aha, so the integral of dx over 1 plus x squared is inverse tangent of x plus a constant, right? The integral of dx over 1 minus x squared is inverse hyperbolic tangent of x plus a constant. And finally, the integral of dx over the square root of 1 minus x squared, well, that's, inverse sine of x plus a constant. So this is a pretty comprehensive list of, elementary integrals. Now, we could unpack the first thing I wrote, right? The first thing I wrote is actually dozens of examples, right? So we actually have to kind of unpack that in practice, but, that's it. And what are the basic rules of integration? Basic rules of integration are this: the integral of f plus g dx is equal to the integral of f dx plus the integral of g dx. We have that. And we also have the rule that we can pull a constant out. Last time we saw that if we had two antiderivatives for the same function, they had to differ by a constant, right? That's why we're always adding a constant here to make the indefinite integral the quote-unquote most general antiderivative. So There's a few others we could add to this list. If you read my notes, you'll find out like there's one for inverse hyperbolic cosine and a few other. I'm sure I'm forgetting something here, but that's a pretty good list. All right, so let us return to your sheet. We got to number 9 last time, right? Well, I say we got to, but I mean you and Audric got to. And by the way, I wasn't joking about the writing dx. Like, writing dx is important. Is a bad habit that Audric has gotten into, which I will cure him of. There comes a point in this very course that not writing the dx will get you into trouble with the calculation. It is important to indicate the variable of the integration. All right. So you guys so we should work on number 10, is that right? Yeah. All right. All right, so we're supposed to do the integral of 3 to the x plus x squared dx. So my opening move is to break it into 2 pieces, right? This is 3 to the x dx plus the integral of x squared dx, right? Now, 3 to the x dx, that's an elementary integral, right? Let's see here. I think it was about the second one I wrote, wasn't it? So 3 to the x, basically it's just a equals to 3. So to do this one, we're going to do 1 over the natural log of 3 times 3 to the x. That's the integral of this piece. This is n equals 2, right? So I do plus what? Plus 1/3 x cubed plus a constant, right? And there it is. How do we check our answer? Like, I don't believe in checking answers. Well, maybe you should. Check answer. Now, we can't always check answer. Like, I could tell you to check your answer for differentiation, but how would that go? There's really, I mean, there maybe are some things you could do, but checking answer is not something we could really do for differentiation, right? But checking answer is something we can always do for integration, because we just have to differentiate the alleged answer. d dx of 1 over log 3, 3 to the power x, plus 1/3 x cubed, right? So that gives me 1 over log 3 times the log of 3 times 3 to the x, right? Plus 1/3 times 3x squared by the power rule. But you see what happens, the 3 and the 3 cancel, the log 3 and the log 3 cancel, and we're just left with 3 to the x plus x squared, right? That has to happen if you have integrated correctly, right? If you've integrated, oh man, I've left all my red chalk at home. So sad. If you have integrated correctly, when you take your answer and you differentiate, you must get back to here, right? That's the way this works. The antiderivative, when differentiated, should give us back the derivative again, right? And the indefinite integral is just a particular antiderivative plus a constant anyway. So same song and dance. Any questions? You might wonder, is there a way to derive integrals, right? Like, is there a way to like calculate it without guessing? The answer is yes, but it's truly horrible. I have like one example of it that I can get through. So generally speaking, we just have to guess. All right, so here we go. Integral, number 11, of x plus 2 squared x cubed dx, right? So did I write down anywhere here like the integral of f times g is like integral of f dx times the integral of g dx? Did I write such a rule? I did not write such a rule. Why did I not write such a rule? The answer is because there is no such rule. This is not even the case. That's not even true for differentiation, although I saw that on the test too. At least one of you differentiated a product as a product of the derivatives. This is not how it works, right? We have to do the product rule. But anyway, that's irrelevant to here because we're integrating. So what you got to do here is just do algebra before you try to integrate. Just expand it out. So let's see here. So x plus 2 squared is x squared plus 4x plus 4. I'm laughing because I think that was on my algebra test this morning. X cubed dx. All right, so integral of x to the power 5 plus 4x to the power 4 plus 4x cubed dx. We integrate that term by term, right? What's the integral of x to the 5th? By the power rule for integration, that is 1/6 x to the 6th. All right? We only have to add the constant once at the end, by the way. All right? You might wonder, like in this one, why didn't I add like plus c1 when I did the 3 to the x, and why didn't I add like plus c2 when I did the x squared? Well, if I had done that, I would have had like a c1 and a c2, c1 plus c2, and I could have just relabeled that c in the end anyway. The point is to add a constant too. Well, I'll explain why we're adding the constant more here in a bit, but let's get through a few more of these on the worksheet. So 1/6 x to the 6th. How does the plus what? The 4 we pull out, and x to the 4th integrates how? X to the 5 over 5. So I get 4/5. Add 1 and divide by that number. And then what do we got? What function, when I differentiate, gives me 4x cubed? Think about it. What function, when I differentiate it, gives me back 4x cubed? X to the 4th. Very good. So this last term is just x to the 4th plus a constant. And there you go. That's the integral. Now, how do you check it? In the interest of time, I'm not going to check all our answers today, but I would point out that if you differentiate this, right? Now, I don't recommend trying to differentiate this and see that it's that. Like, that's not going to go well for you. What you would want to do is to differentiate this and see that you get back to here, right? If that's happening, then at least you did the integral right. You could still be wrong if you multiplied it out wrong, right? If you did the algebra steps to start with wrong, you could still be wrong in the integral, even if the differentiation checks, but, you know, you're only as strong as the weakest link. Let's see here, so, number 12? Uh-oh. Oh, we're good. We're integrating 3x minus 8 plus e to the minus x dx. So I'm going to do one of these deals here because don't have a lot of board space. First of all, I've got 3 integral of x dx, right? Minus 8 times the integral of dx plus the integral of e to the minus x dx. We can break it into these. Think about these 3 pieces, you know. I don't always write down this step because I don't, you know, like in the last example, I didn't write down this step. Do you need to write down this step? I mean, it kind of depends whether or not you understand. if you can do this step in your head like I did here, it's kind of okay, right? But I'm writing it out. So the integral of x dx in this example is 3 times 1/2 x squared, right? What's the integral of dx? So notice that, like, the integral of dx is just another notation for the integral of 1 times dx. So the question is, what function can you differentiate and get back to the number 1? Well, that's just x, right? The derivative of x is 1 with respect to x. So that's why we do minus 8 times x here, because the integral of dx is x. That's something that's important to know, because if you forget it somehow and you can't think through it, people can get really, really stuck on that for whatever reason. And then to make an educated guess on the last one, I'll say plus e to the minus x, right? And then I'd be wrong, because what happens if you differentiate e to the minus x? Right. Yeah, we get e to the minus x times d dx of inside function, which is minus x, right? So that's minus e to the minus x by the chain rule. So if I differentiate this, I don't get back that, right? So I can't put plus e to the minus x. I have to do minus, right? And don't forget, we're doing an indefinite integral, so I still got to add the constant, right? But there you go. That's it. (13) Integral of what? Integral of the cube root of x times the square root of x divided by x. So what's a good way to do this kind of problem? A good way to do this kind of problem is to convert everything over to exponent notation, right? So what we're looking at is x to the 1/3 times x to the 1/2 times x to the minus 1 dx. Cube root is the 1/3 power, square root is the 1/2 power, and dividing by x is multiplying by the negative 1 power in x, right? And then we add exponents, right? So what's 1/3 plus 1/2 minus 1? Put it all in terms of sixths, right? We got 2/6 plus 3/6 minus 6/6. There was 5 minus 6. I believe I have minus 1/6, right? So we can use rule number 1 that I wrote today, right? We've got, let's see here, so x to the minus 1/6 plus 1, right, divided by minus 1/6 plus 1 plus a constant. Now we should simplify that. Don't leave it like that. That's just very lazy to leave it like that. So 1 minus 1/6 is 5/6, right? And 1 over 5/6 is what? It is 6/5, yeah? So what we got here is 6x to the 5/6 divided by 5 plus a constant. That is the civilized way to write your answer here. So, questions? No, the next two are really, really easy. You guys tell me, what is the integral of dx over 1 plus... By the way, this notation just means, that's just another way of writing this, right? Just for the record, like when you write dx like that, that's just a shorthand for what I wrote here. So don't be mystified by that or anything, okay? It's just a convenience of notation. Anyway, what is that? this one and the next one, I've actually written the answer for on the board already. See? Since the derivative of inverse tangent is 1 over 1 plus x squared, the integral of 1 over 1 plus x squared is inverse tangent of x plus a constant. So the first one we got and this one, likewise, inverse sine of x plus a constant, right? Because the derivative of inverse sine is 1 over the square root of 1 minus x squared. 16. Integral of 2 to the x plus 3 to the x dx. How do we do this one? What's the integral of 2 to the x? It is 1 over the natural log of 2 times 2 to the x. What's the integral of 3 to the x? It is 1 over the natural log of 3 times 3 to the x. And then we add a constant because, we're doing indefinite integration. Aha, ooh, look at this next one. Looks kind of scary, doesn't it? Integral of tangent x, secant of x plus 2 dx. All right, so we can break this up into two pieces, right? Like that's the integral of secant x, tangent x dx, plus twice the integral of dx, right? But we know what function differentiates to secant tangent? Well, secant, right? Secant differentiates to secant tangent. So the integral of secant tangent is just secant of x. And what's the integral of dx? We just talked about that. It's x, right? So we have secant x plus 2x plus a constant. That's how it goes. How about this next one? So these are, these are kind of silly because I wrote the table on the board today, huh? So the answers to these are actually already on the board. Right, the integral of secant squared is tangent because the derivative of tangent is secant squared, right? The integral of secant squared is minus cotangent because the derivative of cotangent is minus cosecant squared. Oh, and then 20, integral of dx. See, I put that there just in case I forgot. Integral of dx is x plus a constant, right? There we go. So, this anti-differentiation game, it's a fun game to play, right? But at some point, you want to ask the question, why are we doing this, right? So the ultimate reason that we're doing this is to address the area problem. Do you guys know what the area problem is? What's the area problem? Did I talk about it? I think I probably talked about it a little bit at the start of the course, unless I got distracted somehow. But there are really two problems that Calculus 1 addresses overall. The first problem is how to describe the tangent line to a curve, right? And we've answered that question, haven't we? The answer is you differentiate the function. That gives you the slope of the tangent line, and you can put it together, right? So we already answered the tangent question, but there's another question, which is the area question. So the area problem basically is just this. So here, here's the most plain Jane version of it. A, B, like this. You know, you've got some function y equals f of x. The question is how to find this area. This is the area problem. So how would you guys do it? When I was a little kid, sometimes if I was in a room that had like a floor kind of like this one, I would start trying to calculate the area of the room by doing what? So if you wanted to calculate the area of this room, if I told you that these tiles were foot by a foot, right? Or 10 centimeters by 10 centimeters, well, that's not true, they're not that, but if you look down at the, what's that? Well, that's true. The integral is going to describe this, but that's not at all clear. It's not at all clear what this undifferentiating that we're doing over here has to do with that area problem over there, is there? See, because why should the opposite process of differentiation have anything to do at all with area? I mean, this is a very bizarre claim that I'm making. I would say that the most sort of like elementary way to think about area, and we've been doing this since the ancient times, is just to take an area which is complicated and divide it up into like little pieces which we know have a clear understanding of how to describe area, right? So if you have like a little rectangle, the area is length times width, right? So if you could somehow take this area, right, and then like divide it into like little rectangles, or bigger rectangles, you know, and you could, you know, like just find little rectangles that are inside it, and you can calculate the area of all these little, you know, rectangles, like that. That would, if I could find the area of this one, 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 and this one, add those up, that would give me a pretty good approximation to the area under the curve, right? That's the idea. But again, it's a profound mystery what on earth that has to do with anti-differentiation. The answer to that question is given by what's called the fundamental theorem of calculus. So we'll prove this next week, but what we'll learn next week is that the integral from a to b of f of x dx, it's equal to f of b minus f of a. So this is what we're going to explain next week. This is the fundamental theorem of calculus, part 2. Fundamental theorem of calculus 2. Just to give you a preview of this, suppose you want to find the area under x squared, right, from 0 to 2. So here's y equals x squared, right? Fundamental theorem of calculus says you can get this area by calculating the integral from 0 to 2 of x squared dx. So this is that same notation we were using. This is an antiderivative for that. What's the antiderivative of x squared? We've already learned it's 1/3 x cubed, right? Yeah. And then you have to take this formula, right, and evaluate it from 0 to 2. What that means is 1/3 of 2 cubed minus 1/3 of 0. The answer is 8/3. The area under this curved shape from 0 to 2 is exact. Now, this is not an approximation of the area. This is an exact account of the area under that curve. So this is the main reason that we care about antidifferentiation in this course, because it, through the magic of the fundamental theorem of calculus part 2, allows us to calculate areas under curves. Why this is true is a profound mystery that was hidden from the ancients, and this is what distinguishes Newton and Leibniz from their predecessors. Like the professor of Newton, Isaac Barrow, I think his name was, he understood things about tangents. And there are other people that understood aspects of this mystery, but no one put it all together like Newton and Leibniz before them. That's why they're credited with the discovery of calculus because, you can go back to like Archimedes, like 2 millennia ago. He had ways of calculating area under curves or in complicated geometric shapes by dividing them up into pieces and getting better and better and better approximations, right? But it takes just a colossal intellect to do that kind of calculation. This here, we could teach to middle schoolers if we had enough time. It's not hard at all. Like, calculus is not hard once you understand it. It's really just algebra, right? Like, the mechanics of what I'm doing here is no harder than factoring. It's easier than factoring, good grief. It doesn't require guessing at all, actually, once you know that anti-differentiation rule. Okay, so that's the area problem. That's one of the reasons we're anti-differentiating. But there's even a more basic rule, right? Think about this. Physics. Another motivation. The other motivation is solving differential equations. Let me kind of tell you what I mean by that. So physics is a good example. Remember, we had x, we had v, we had a, right? X was the position, v was what? The velocity, that was dx dt, right? A was the change in the velocity, dv dt, or of course you could say d squared x dt squared, right? So to go down this list, you take derivatives, right? To differentiate the position gives you the velocity. Differentiate the velocity gives you acceleration. So this way, differentiation. How do you go the other way? Integration. Now there's some strings attached, right? There's some strings attached. Let me give you an example. So suppose the velocity is 3t minus 8, right? Find possible position x as function of time. So we're trying to figure out what we know is we know that dx dt is equal to 3t minus 8, right? So what's the question we're asking here? We're asking the question, what function x, right? What function x can we differentiate to get 3t minus 8? What is that? That's the indefinite integral, right? So x is going to be the integral of 3t minus 8. I mean, that's just, this and that are like logically equivalent. Because to say that x is the integral of 3t minus 8 is to say that x is the function that when differentiated gives you 3t minus 8. What is the integral of 3t minus 8? Well, we could do that, right? It's 3/2 t squared minus 8t plus a constant, right? You're like, well, that's weird. How can we have a specific velocity and yet the position is only known up to a constant, right? Well, if you actually stop and think about that for a minute, it's not surprising at all. I tell you, I tell you my velocity is a function of time, and then I say, well, where what was my position when I started an hour ago? You wouldn't know unless you actually knew my position at some other time. You have to have a starting point to set up the position, so to speak. So to figure out what that constant is, we need more data about the problem, right? So you guys tell me, like, if the position at time, let's say 0, was equal to 10, then x of 0 is what? 0 plus, like when you plug in time 0, into this formula, what happens? The stuff with 0 just goes away in this case, and you're left with a constant, right? So that constant would be, we would choose the constant equal to 10 if that was the data, this was the initial condition. If the initial condition is x of 0 is 10, then we find c equals to 10, and the position would literally be x is equal to 3/2 t squared minus 8t plus 10. Yeah? So this is the other reason that antidifferentiation is interesting. If you give me velocity, you antidifferentiate to find the position. If I give you acceleration, you can antidifferentiate to find the velocity, right? Now, to find the specific velocity as a function of time, to find the specific position as a function of time, you also need to be given an initial value, an initial condition. Otherwise, you get like plus the constant in your answer. The reason that there's plus a constant in the answer, a way to think about it physically speaking, is this addition of the constant allows for all possible initial conditions to be implemented. That's the way I think about it from a physical perspective. But of course, we don't have to just do physics, right? We can look at it purely as more of a mathematical problem. That's the next one on the worksheet that I'll do. All right. Let's see here. So here's sort of a concept. If we're integrating dy dx with respect to x, we just get y. The integral of the derivative is the function we're differentiating. So that's a useful calculational concept as we face number 21. It'll kind of like, I mean, I said to you in the previous example that these were logically equivalent, you know? But saying that is not as nice as giving you a formula to implement that. And the formula to implement that is what I just wrote next to concept, right? So like, let's see here. So 21, we're supposed to solve dy dx equals to 3x minus 1 given y of 0 equals to 2. So we'll keep the y of 0 equals to 2 in mind, all right? We basically save that for the end of the problem. We'll implement that last. So what you can do with this sort of thing is say, aha, well, this means that the integral of dy dx is equal to the integral of 3x minus 1 dx, yeah? But this is just y again. By the way, did you guys notice that I put numbers on the area discussion on the integral? But I'm not now. That's because these are different kinds of integration. I should have mentioned, by the way, this is a definite integral. It's called a definite integral. In contrast, the one I'm doing in this current example is an indefinite integral. An indefinite integral, the answer for an indefinite integral is a set of functions, actually, right? It's a function plus a constant, an antiderivative plus a constant. In contrast, a definite integral, if it exists, the answer is a number, all right? So they're rather different calculations, even though we both use this funny-looking symbol for the integration in both cases. Do you know why that integral, what that symbol's for? that it's actually a cursive S. It's for sum, which I'll explain more next week. Again, admittedly, why is this a sum? That is not clear at the moment, logically, why we're using a sum symbol for the antiderivative. Okay, anyway, so you guys tell me, what's the answer here? Yeah, x to the power 2, the 3 stays there, right? Divided by what? Yep, divided by 2. That takes care of the first term, and then what's minus 1 integrate to? What function? Yeah, minus x. Very good. And then, of course, we have to add a constant, right? And that constant is what gives us the freedom to implement this condition. This condition, it's going to fix the value of c. That's what's going to happen. So y of 0 is 3/2 0 squared minus 0 plus c. That's equal to 2. So this tells me c equals to 2 in this case. Don't always assume that c has to be the value of the initial condition. That doesn't have to happen. I put it at 0, you know. What would have happened if instead of giving you at times 0, I'd given you, at x equal to 0. If I just put, instead of putting a 0 here, I'd put like a 1 here. That would have changed the game, right? So anyway, just saying. Think through this. Don't just assume that c is equal to y of 0. That doesn't have to always happen. All right, so anyway, the answer, y equals to 3/2 x squared minus x plus 2. There you go. What we have done here is to solve an initial value problem, right? So antidifferentiation allows us to solve initial value problems. Let's work another one. 22, I've got dy dx equals cosh of x, hyperbolic cosine, given y of 0 is 7. So we have y is the integral of cosh x dx, right? That's the key idea. We integrate the derivative to get back the function. And the derivative is also equal to cosh, so we can integrate cosh, right? Integral of cosh is sinh plus a constant. So then we have y of 0 is sinh of 0 plus a constant. What is sinh of 0? Nope. Sinh is e to the, sinh of x is e to the x minus e to the minus x all divided by 2. So if you plug in 0 into that, you get 0. So sinh of 0 is 0, much like sine of 0 is 0. And so we get c equals to 7. So I think maybe the next example I'll finally escape this pattern here. But anyway, this one is y is equal to sinh of x plus 7. There you go. We have the velocity is given by, and so sometimes I write v of t to emphasize that the velocity is a function of time. That's not v times t, that's v as a function of t. And a lot of times I omit that of t there. but I'll write it this time just for the sake of diversity of notation, I suppose. So 3t squared minus 8t is velocity. And we're given x equals to 3 when t is equal to 1. So this can also be expressed, as I did in the problem, as x of 1 equals to 3, right? We're supposed to find the position as a function of time. So what are we looking at? We've got dx dt is 3t squared minus 8t, right? So we integrate both sides. What does it give us? Integrating both sides gives us x is the integral of 3t squared minus 8t dt, right? Now you guys help me out. What's the integral of 3t squared? What function can we differentiate and get back 3t squared? T to the third, very good. And what function, what's the integral of minus 8t? What function can I differentiate and get back minus 8t? All right, guys, so it's minus 8 times t squared over 2, right? Because the integral of t is t squared over 2. I'll clean it up a little bit. That's t cubed minus 4t squared plus a constant, right? We're not done because we don't want that constant in our answer, right? And we know that when t equals to 1, right, x of 1, which is 1 minus 4 plus c, well, that's equal to 3, right? That's the given initial data. So what's minus 1? So that's c equals to what? C equals to, solve for c, right? What do you get? Yep, 6. C is 6. So then the answer, x as a function of time, is t cubed minus 4t squared plus 6. Now, all of these physical examples I do in this course, they're sort of tasteless from a physical perspective in the sense that I'm missing like dimensional multipliers. You know, physicists care about units, and they have to put letters that bear the units of, you know, the problem. So my examples in here are always kind of stripped of units for the most part, just to focus on the math and not get distracted by, you know, feet versus meters versus all that kind of stuff, right? So I'm going to take a slight break here from the formula sheet because there's a thing that I just feel like it belongs in this lecture. So you guys know the kinematic equations from like high school physics, perhaps? How does it start? Constant acceleration, right? So we have constant acceleration of minus g, right? And so here I'm talking about the case. We've got y is the position, right? Then v is dy dt is the velocity. And then a is the acceleration. This is all with respect to the vertical direction, right? We're talking about gravity. Okay? And let's assume that y of time 0 is y sub naught. And let's assume that velocity of time 0 is v sub naught. All right? So if you integrate this, what does it give you? I mean, a is minus dv dt, right? Is minus g. Integrate that, we get v is equal to the integral of minus g dt, which is what? G is a constant here, right? So that's minus g times time plus some constant, right? But v of 0 is v naught, which is equal to minus g times 0 plus c. C is v naught. So this gives us that the velocity is the initial velocity, v naught, minus gt. This, is, of course, is one of our beloved kinematic formulas in physics, right? For a constant acceleration problem under gravity, you have the initial velocity minus gravity times time. That's the velocity in the y direction. But what else? That is equal to dy dt, right? This is equal to dy dt. So I can integrate this with respect to time again. And I get y is the integral of v naught minus gt dt. Keep in mind that v sub naught and g, these are just numbers, they're just constants, physical constants, right? And so this is v naught t minus 1/2 gt squared, right? Because the integral of t is 1/2 t squared, as we've seen today. Maybe with x instead of t, but we've seen it a couple times. Plus a constant, right? And I probably should say c2 because I already used constant. Maybe I should call this constant 1. You know? Anyway, constant 2. What do we know? We know y of 0 is equal to y naught, right? But that's also equal to v naught times 0 minus 1/2 g times 0 squared plus c2. Of course, all this trash is just 0, and we're left with y naught equals to c2. Lo and behold, we have derived y of t is equal to y naught plus v naught t minus 1/2 gt squared. This, of course, is another one of the famed kinematic equations that we study in high school physics or university physics, right? But university physics, at least we've had calculus, so we can derive it like I just did, right? Without calculus, you can't really derive this. This is the other reason that Newton was studying calculus, is because he wanted to understand the physics of motion, and he understood that to understand instantaneous velocity, you need calculus. All right. Anyway, so these are, yeah. All right, let me return to the sheet. All right. What are we going to do here? I guess we should multiply it out, right? So we use the distributive property, which should give us 6 terms. We've got a binomial times a trinomial, 2 times 3, 6 terms. So looks like we got an x cubed plus 2x squared plus x minus 2x squared minus 2x minus 2. That's 4x rather. So 2 times minus 2 minus 4. Yeah. We can collect like terms, right? So we've got x cubed. Oh, those cancel, don't they? That's nice. And minus 3x, yeah.